Thanks a lot, Sean, for making this happen. It's good to be here. So this is related to Michelle's talk, but at the same time, my primary interest in this is actually control. Information theory turns out to be a useful analysis tool, but I'm interested in fundamental limits of control in general. And by the way, limits of control, again, stole the title from Jim Jarmusch. It's a great film. And the main character always drinks 2 single espressos at a cafe. Anyway, so this work is actually a year or so old, but I'm still thinking about this because there are nice implications that I've started exploring with Sean and with our joint student Epsilon, who's actually sitting right here. I'm not going to talk about those results yet, but this certainly feeds into that. So we're going to look at adaptation, right? Because control is tied to adaptation, which is a big feature of cognition, and any complex system should be able to adapt. What do we mean by adaptation? So, one of the sort of big name worthies in control, George Zames, who was at McGill. I guess Sean has probably taken courses from him at McGill. He had an interesting viewpoint about adaptation and what it meant in the context of control. And actually, I think it's easier for me to stand here. So to Zames, adaptation and learning were synonymous with acquisition of information in the process of controlling a system. So control is sort of a primitive notion, like a notion of point in Euclidean geometry. It's just there. It's something you want to do. And adaptation and learning are a feature of a system that is good at controlling, or is good at carrying out the control goals. So what do we mean by information? So this is not information in the Shannon sense. In fact, I don't think George Zames would have wanted information to be understood in the Shannon sense. And according to Peter Keynes, when I gave a similar talk at McGill, he said that George probably would have fought you on this quite a bit. But I think I preserve enough of the spirit of what Zames was talking about. He was saying information about the system that is relevant for control is metric, meaning that you have some uncertainty about what the system is, and you can visualize this uncertainty geometrically. You could say, I have some sort of a model about my system, and this model is based on intuition, domain knowledge, previous experimentation, what have you. But I don't trust it too much, so I draw some sort of a ball around that model in a suitable metric, and I say, well, really the system that I'm dealing with could be anywhere in that ball. And this viewpoint has actually originated in control theory, but has somehow made its way into economics. Actually, there's a book by Thomas Sargent and Lars Hansen called Robustness on precisely this viewpoint applied to economic modeling. So the notion of information is metric, and then there's also the element of time, right? So as you're controlling the system, presumably what you're doing is you're shrinking the size of that ball, because as you get more information, you're able to eliminate some uncertainty about the system that you're controlling. So non-adaptive control doesn't make use of that. It's just something that you design beforehand, and you don't try to explicitly reduce your uncertainty as you're controlling the system. Adaptive control is something that actually does actively try to shape its own uncertainty by trading off acting on the system to carry out the control objective versus exploring the system to maybe reduce uncertainty and buy your and then that way you buy yourself some control capability later. So in this talk, what I will do is try to present kind of a meta-theorem that quantifies the trade-offs between a priori information, which is geometric information in the sense of Zames. It's not stochastic uncertainty, it's geometric uncertainty about the system. The information that you acquire as you're controlling the system, and the translation of initial uncertainty and acquired information into a reduction of uncertainty a posteriori. So as you keep going, and I'm going to show how this meta-theorem actually allows you to derive fundamental limits on system identification, and also gives, and I'll show how to derive lower bounds on the rate of adaptation of controlled of unknown linear system. Actually, that's an old result, but the proof is typically very hairy. It involves, pages of multidimensional integration. It's character building, but not intuition building. So so I think I'll try to simplify that proof and see what information theory can do for us. So,
Max?
Yes.
So when you talk about a priori information uncertainty, are you talking about model uncertainty, or are you talking about uncertainty about state?
I'm talking about model uncertainty.
Okay.
Right. So stochastic dynamical system has some input space U, which is your control space, and it has output space Y. I'm not looking at partial observations here. This is full information case. Not looking at partially observed systems. So we have basically a system is described by a collection of probability kernels. I'm not even looking at first order systems or Markov systems. This is quite general. What we have is at each time we have the output at time t potentially determined by all the previous outputs and all the previously applied controls. So that's a stochastic system, and there's a parameter theta which describes the system, locates the system in some metric space. Right, so this is just a fancy notation for the probabilistic description of the system. So if I knew the history of the system up to time t, then I could predict where the system is going to be at time t. Right, and so what we're going to do is we're going to place this parameter theta in some metric space with a metric row, and that is a modeling kind of a choice, right? So when you design your system, or when you're trying to design a controller, you typically assume something about the system structure, and this is part of the problem specification. And then we have controllers. So this system by itself is just a collection of building blocks or stochastic kernels that tell you if you apply certain inputs to a system and it has had certain sequence of states, this is where it's going to be. In order to realize the behavior of the system, you have to interconnect it with a controller, right? So you need to have something that gives you the control input at time t, given the observation of the system up to time t, plus memory of past controls. Again, I'm not simplifying anything. I'm not insisting on Markov controls or stationary controls or anything like that. So controllers are stochastic, and gamma is some sort of an index for the controller. We're not interested in putting that in the metric space. It's just some sort of an index to keep track. Just name the controller. We have some controller gamma, here it is. But it could also represent some structural constraints. Okay, so once we have the system and the controller, putting together these transition probabilities defines a well-defined probability measure, and you can play all sorts of games with Ionescu-Tulcea consistency theorem under the right technical conditions. This defines a well-defined joint probability distribution on sample paths of states and inputs at time t, at any time t. Right, so this defines a probability distribution which is indexed by the system parameter theta and by the controller choice gamma. So actually there's a very insightful paper by Hans Witzenhausen on separation of estimation and control, and it basically says that your system behavior does not become a random variable until you specify the controller, right? Because that interconnects the kernels governing the system right here with the control law, and then by the appropriate consistency theorems, then everything becomes a well-defined random variable. Okay, so how do we acquire information? Well, let's think about identification. Suppose that we have a control system that's running and it's doing its thing, and then somebody comes in and kind of reads off the signals and tries to identify the system based on the path that it traces through input-output space. So I'm not necessarily saying that we're actually doing identification, but the question is, if I'm controlling a system, how well can I identify it? because there's actually a trade-off. If I have a really good control that drives the system to some really boring state where you want it to be, because I mean, often that is the goal of control, to make things as boring as possible. Identification is not going to help you much because you're in a boring region. The system doesn't really do anything. It's near zero. So what can you identify? Systems near zero look more or less the same, you know, within a certain metric space. So there's going to be a conflict. There's going to be a tension between difficulty of identification and difficulty of controlling. So suppose we have an identification algorithm, and it's some sort of a mapping. You give it a history of what the system was doing as it was being controlled, and it tries to determine what the system was. So what we want to do is we want to take a given controller, and then we'll say, well, I think that my system is actually in some subset lambda of this larger metric space theta. That's my initial model uncertainty. So if I think that that's the case, I have an identification algorithm. All it does is produces an estimate, and I'm looking at identification error. So this is that metric that you have on your original system space, right? And then your algorithm spits out estimate theta hat t, and you compare it to the real system, right? And the expectation is actually with respect to the measure induced by the true system and the chosen controller. But what you're doing is, since you don't know what the true system is, you're trying to make the best of the worst situation. So it's a minimax type of a thing. So in general, you would expect that if gamma is a good controller, meaning that, you know, it drives the system to a boring space, to a boring place, then this identification error will be large, right? Because if the controller is good, it kind of prevents you from learning too much. And so the point is some classes of systems are easier to identify than others. And then there's something that control theorists have long called the dual effect. Now, I think that goes back to the work of Feldbaum from the Soviet Union. And the idea is that that's precisely what I just stated. There's a tension between controllability and identifiability, meaning that if you are good at controlling the system, you remove all the uncertainty that an identification algorithm should be able to exploit to say something about degrees of freedom in the system and system parameters. So let's see how these things interact. So there's a basic lower bound, which is actually, which kind of sets things up. The proof is ridiculously simple. It's just triangle inequality and Markov's inequality. But the idea is, but the implication is actually quite interesting. So in a way, system identification. So this is actually a reduction, what Michel was talking about. This is reduction of system identification to hypothesis testing. And here's what I mean by that. So suppose this is our uncertainty set lambda. And suppose that I know a priori that my system, the parameter, is not just an element of lambda. It's actually one of finitely many points in lambda. And these points are separated in this metric row by at least epsilon. And then you can actually lower bound this identification error by something that is proportional to the separation, which is epsilon here. And now this is not identification error anymore. This is probability of incorrectly identifying the system, assuming that it's in the subset S. So before, wrong way. Before we had a metric notion of error. Now we replace that by more of a guessing notion of error. Probability that you incorrectly identify the system. Okay. So now this is interesting because if I make this epsilon small, I'm necessarily, so if I make epsilon small and I try to look for a large epsilon separated subset, well, the smaller the epsilon, the larger a subset I can find. And the more hypotheses you have to distinguish, typically the harder the task becomes. So there's going to be kind of a tension here. If I make this epsilon large, this probability will become small, but then the overall error might increase. If I make this epsilon small, then I could find a really large epsilon separated subset, and that will, again, make this probability of error large. So let's see how these things interact. So this is where Zames brought in ideas from fundamental work of Andrei Kolmogorov on complexity of function spaces. the complexity of metric spaces. So the idea is that I have a metric space theta, and for any set lambda, I can define something called the epsilon packing number, which is the largest number of elements in that set such that they are separated in that metric by at least epsilon. So it's a packing notion, right? This is lambda, and I pack balls of size epsilon into lambda, and I'm looking for the largest number of such balls that I can fit in lambda. So the Kolmogorov epsilon entropy is the log of that number. So this is, now we're kind of entering some information theoretic territory. You can think about the situation where suppose you're using a fixed rate transmission and you want to identify one of these centers of these balls, so you can use this many bits to do that. So now we're going to reduce our control problem to hypothesis testing with feedback. So this is our class of systems, and we have some sort of a controller. We want to certify that controller. So now suppose that, how do we certify that controller? We're going to pick a large epsilon separated subset. So it's going to be the maximal packing with separation epsilon of this lambda. And now suppose that we have somebody who wants to certify the controller to see how well that controller does. So what we're going to do is we're going to pick one of these systems uniformly at random from these centers, and we're going to let the controller work on that system. We don't tell the controller what the system is. The controller does its thing. So that means that what we do is we interconnect theta sub w, which is a random choice in this packing set. And that's interconnected with the controller. That whole thing runs for time t, generates this kind of a history, right? So that means that here, this is just a formal way of specifying the probability space. And I already said in words what it means. We just choose a system at random and let the controller run on it, right? So, and then we have an identification algorithm. Some sort of an algorithm that knows that, in fact, the system is one of these n theta sub i's, and looks at the sample path, looks at the history of the controls and outputs, and tries to guess the system. So what we're going to see is an interplay between the best performance of an identification algorithm for a given controller and the amount of information contained in the amount of uncertainty about where this true system is and how much information is generated during the control process. So there are three kinds of information. The first kind is a priori information, and that's Zames, metric complexity of the system class. And then we have a posteriori information, and that's the probability of correctly identifying the system after time t, right? Because the idea is that if you were doing a good job, presumably you're going to have less uncertainty about the system after you're done controlling it for a while than you had initially. And then there's information acquired online. So that is actually what gives you a reduction from this to this, right? The more information you acquire online, the faster you're able to reduce uncertainty, and therefore, presumably, that will make your identification probability performance better. So we will quantify online acquisition information actually using Shannon's information theory, right? So what we're going to do is we're going to look at the mutual information between the random system choice, which is not revealed to the controller, the state at time t, and the information, and this mutual information is actually conditioned on the information available to the controller at each time t. So at time t, this is basically the reduction of uncertainty about the system. So let's see how that plays out. So, well, I can actually skip these slides.
One quick question.
Yes.
Why the mutual information to y?
Because
some people might imagine it would be z at time t, for example.
Well, well, if it's z at time t, z is yt, ut is chosen on the basis of y. That doesn't add any information by data processing.
Basically the same thing as z.
It's basically the same thing as z. Yeah. So I'm going to skip these slides because I was actually giving this to graduate students in aerospace. So this will insult your intelligence. You don't want to see that. Okay, so here's the meta-theorem on identification and control. So any controller gamma and any identification algorithm theta t, so the controller, I could tell the controller actually the system is in a finite set. So grant some side information to the controller and to the identification algorithm. And then you see that the product of the initial uncertainty, which is this metric entropy, and the minimum probability of correctly identifying the system after time t is bounded by the sum of terms that are related to information acquired online. Here, there's a degree of freedom, which is the choice of this auxiliary probability distribution of y at time t given z at time t minus 1. If you've seen the work by Yuri Polyansky on converses, this idea of using auxiliary distributions as a degree of freedom in lower bounds or in converse is a very powerful tool. So, so this is kind of an uncertainty principle if you think about this. This is a trade-off between initial uncertainty and final information gain, right? Because the smaller this quantity is, the more information you've gained. And this is controlled by how much information you can acquire in the process of controlling the system.
So is the right-hand side in some sense a fixed quantity?
No, the right-hand side, not necessarily. So strictly speaking, what you should be doing is you should take the infimum over all possible choices of q, right? So that'll give you the tightest bound. But on the other hand, carefully picking a good q actually gives us a handle on what's happening. For example, I could pick q to be a controller based on the identification algorithm, or I could pick q to be a measure induced by some nominal system and compare it to what the actual system is actually doing. So there's some freedom of choosing q that you can actually exploit.
Is the bound going the right way?
It is going the right way.
I don't understand your notation, so I clearly needed the graduate student slide. Why are there 3 bars?
Oh.
What does it mean to have an extra bar in the?
That's condition. So that's the conditional divergence, which is okay. So here's what you do: is this. If you condition on zt minus 1 and w, you have 2 kernels that 2 probability distributions on the y space, and you can therefore compute the relative entropy between those kernels, and then you just take the expectation, the conditional expectation, then you just take the expectation over what you conditioned on.
Oh, this is the expectation of dpq.
Yes, yes, yes.
With respect to the last thing.
That's right. Yes.
Oh.
So that's actually standard notation in information theory.
Okay.
Yeah. Right.
All right.
So yes. So this bound does in fact go the right way. I'm not as fast as you, Rajesh. Okay. So here's the proof. So basic observation is this: if I were to look at the maximum probability of incorrect identification, that probability actually is lower bounded by the best I can do with any identification algorithm that knows that my system is in this finite set under an average case. So worst case error probabilities are always lower bounded by average case error probabilities with respect to any prior. Here I choose the uniform prior because I know that whoever tries to certify the controller picked a system uniformly at random. Okay, and then since this W is uniformly distributed, we can use Fano's inequality, which actually lower bounds information theoretically the best performance in a hypothesis test. Right, and so we have the mutual information between the unknown system index and all the information that's available to the identification algorithm at time t. So you can see the interplay between the log of the number of possible values of W and the mutual information. And then we bound the mutual information using the chain rule, right? So this is that decomposition, sequential decomposition of mutual information. So at time t, I can look at how much information I gain with a new observation given what I already know, and the overall information is the sum of these contributions. And then you can use a very nice relationship that you can basically upper bound mutual information using terms like this by varying this distribution Q. So that's because there's a variational representation of mutual information represented as an infimum of this. And so you just rearrange to finish the proof. And so once you set everything up in just the right way, the proof is ridiculously, embarrassingly simple. But what are some of the implications? For example, we can talk about lower bounds on identification error. So I'm going to use some shorthand. So P sub theta T is actually this conditional distribution. So now we have, again, a pair. This is our uncertainty set lambda. We have a controller gamma. And suppose that actually there is a sequence of identification algorithms that has a that has a given performance, meaning that if I look at what happens at each time little t and I try to identify the system, this is how well I can do in a sense of relative entropy in the worst case. Then actually it implies a lower bound on this identification error determined by the critical separation. The critical separation is an interesting quantity. This is your initial uncertainty about the system, where you choose a separation radius, this sigma t, in such a way that it balances out the information that you gain as you're controlling the system. So, so what you do, so this is where the choice of q is actually useful. So at time t, so the q, the only constraint on q is that the conditioning cannot be with respect to the unknown system index. But anything that you can compute from zt minus 1, you can condition on. So why not try my identification algorithm, theta t? That's perfectly valid because theta t minus 1 hat is actually determined from everything I have up to time t minus 1. Then I know that by my assumption on the identification algorithm before, right here, that actually gives me an upper bound on how much information I acquire in time t, and then you just apply the meta-theorem with that critical separation. So now, so it's kind of a game, right? I say, here's my identification algorithm with a guaranteed worst case performance. And the agent who certifies the system says, well, I'm going to pick a packing set with just the right separation that however much uncertainty you had, it's balanced out. However much uncertainty you reduce, it'll take you. Basically, I put in as much uncertainty about the system initially as you could take out with each step of the identification. So therefore, we have this kind of a bound right here, right? This is the metric entropy, because that's how I set up that metric entropy to be, right? That's what I set it up to be. And this is the minimum probability of error. What I did is I basically put in twice as much uncertainty in the beginning as you could extract while controlling the system. So that means that your probability of incorrectly identifying the system has to be at least 1/2. And then you just apply the basic lower bound, right, from our proposition. Right, this is worst case. I know my separation is sigma t, so that's the lower bound. So the idea is to basically, I can play this game. I say I have an identification algorithm that can remove uncertainty at a certain rate. Well, I'm just going to put twice as much uncertainty, and you won't be able to get it all out in time t. So that's how you use that. And this is the nice, judicious choice of this auxiliary distribution q. Here's another thing, and this when I derived this, I was kind of surprised at how interesting this result was. Suppose you have, again, a controller gamma. Well, I don't say anything about a controller, some sort of a good controller, and you have a system of identification schemes and a non-increasing sequence of positive reals. And suppose that, so I'm going to look at systems such that the identification performance, if I look at the kth moment of this metric row, is bounded by these constants beta t. So in other words, I'm looking at all systems for which there exists an identification algorithm whose errors decay in the kth moment, decay at rate beta t. And I want to say, well, how large could my uncertainty about such a system be? And the theorem is this. Suppose that I have a controller such that if I were to identify the system after time t, as it's being controlled by this controller, the rate of error in this relative entropy is actually, again, kth power of my metric in the two possible systems. So in other words, if I were to, this is the true system, theta, But if I were to kind of pretend that actually the system was theta prime, this is how much error I would incur. Then, this is an interesting thing. There's an upper bound on the initial uncertainty you could have had about that system. So the precise interplay between the radius and all these parameters is not important. But what is important is that this is kind of an argument going in the opposite direction. Before I said, if you're really good at identifying the system, I'm going to try and put in more uncertainty you can possibly hope to remove with your control and identification. Here the idea is that if you're really good at identifying the system, and these systems are kind of rigged in your favor, right? They're the ones that you're really good at identifying. Then the class of these systems couldn't have been very large to begin with. So here's my class lambda. And from the smoothness condition that was there before, I can upper bound the amount of information that we can acquire in time t. And then from before, we have this kind of a thing, right? So we know that the error in identification is bounded by this, right? This is the critical radius that you choose. That's my entropy, and that's how we choose it. Now suppose, so this is a contradiction argument. So the idea is that suppose that this entropy was larger than this ht. Then the radius would have to be smaller than sigma t, because the entropy is actually, as you make the separation radius smaller, the entropy increases, right? Because you can pack more balls. So that way, we know that the error has to be at least this much. On the other hand, we know by our assumption that the error is bounded by this quantity. So we derive a contradiction. So it means that our initial uncertainty about the system class couldn't have been larger than how much information you acquired. In other words, it's an interesting kind of a thing. Here what I did is, as I said, I allowed a very good performance on identification, and I rigged the stakes in the controller's favor, in the sense that I said, well, here are all the systems you could possibly identify well with that convergence rate. And the thing is that there couldn't have been very many of those systems. So here's
But Max,
yes.
the controller is not allowed to depend on which system.
No.
So, because you could take a class of systems such that for each system there is a controller that allows you to identify well on your result.
Right, but here the idea is that there's one controller and one identification algorithm. It's all in the minimax sense. Clearly, I can always find a good controller and a good system that work perfectly together. The idea that I take the supremum over the system over the class of systems. So here, the smoothness condition is not just a thing for the proof to go through. It actually applies many cases. For example, here we have a first order dynamical system with some nonlinearity, and we have additive Gaussian noise. And suppose that the system mapping theta is nice and Hölder in this metric k, right? So difference between f theta and f theta prime is bounded from above by some kth power of the metric rho. So then you can actually, if you assume that the controller, so this is an assumption on a controller. If you assume the controller is such that it keeps the system state bounded, then this smoothness condition is satisfied. So it's not exactly just an academic exercise. And here's some interesting implications. Suppose that I have a class of systems that I can identify at this rate, right? So t to the minus alpha. Then that gives me an upper bound on the metric entropy of that class of systems. So in other words, here lambda, so if the errors decay as t to the minus alpha, then lambda has to be basically a ball in an infinite dimensional Hilbert space. In particular, if the decay is t to the minus 1, then your class of systems is actually finite dimensional. So in other words, if we have a class of systems and they're easy to identify, then then you couldn't have had much uncertainty about the systems to begin with. How much time do I have?
Like just under 10 minutes.
Oh, okay, good. So now let's take a look at another concrete problem. We have an adaptive control problem. It's an unknown linear system. Nth order, n-dimensional first order linear system. And we don't know this matrix A, we just know that some matrix with operator norm bounded by 1, and we have Gaussian disturbance. Our goal is to select the controller gamma in such a way that on average the state stays near the noise level. So that's called stabilization to the origin, right? If there were no noise, I could actually demand that eventually this average would be 0. But because there's noise, the best I can do is keep the Cesaro average of the squared state norm near the noise level. So this is adaptive regulation, and it has a very rich history. Osterman, Wittenmark, Goodwin, Ramage, Keynes, Guo and Chen et al. I mean, it's a well-studied problem. Okay, so what's the optimal rate of convergence? Meaning that, how quickly can what is the gap between the performance at time t and this asymptotic figure of merit? So here's an observation. Basically, the idea is that since the state at time t-1 and control at time t-1 are all measurable with respect to the noise up to t-1, they are independent of the noise at time t. So we can basically say that, well, the squared norm of the state at time t is actually, it's just like the regression function argument. You can represent it as a sum of expected error between the state and the noise at time t plus the noise level, right? So that's the idea. So therefore, given the controller, we can consider something called t-step regret. So the regret basically is this quantity, right? So I want that to go to 0. Because if this goes to 0, then this is the remaining term that'll stay in the average. So the question is, what is the optimal rate at which the time normalized regret converges to 0? So previous work on lower bound. So there's a paper by Nemirovsky and Tsipkin and Lai, and as I said, those are character building, multidimensional integration proofs. So there's actually a way to do it much quicker. Okay, but I'm going to assume that the controller supplies what's called persistent excitation, meaning that this Gram matrix is positive definite with a strict lower bound on its eigenvalues with high probability. And a lot of controllers will be persistently exciting. Persistent excitation is needed for you to run least squares. So here's the theorem. If we have a controller that has C delta persistent excitation property, so C controls the eigenvalues, right? So how well conditioned this Gram matrix is. And this is the probability of it not being well conditioned. And delta is less than 1/4. And suppose that at time t it achieves regret of no more epsilon, then at time t has to be at least this much. So n squared sigma squared, that's not surprising because what we have is so n squared comes from the fact we have n by n matrices. So that's the dimension of the uncertainty space. This is the noise variance. And then we have 1 over epsilon log 1 over epsilon. So that's the dependence on this regret. Okay, so how do we do that? Well, so there's a lemma that I'm not going to prove. But the idea is that given a good control strategy, I can construct an identification algorithm, which is not really part of the control strategy. Again, it's a reduction. If I can control well, then I can identify well. So it computes this Gram matrix and just simply does this kind of least squares. So if the controller has the persistent excitation property, then so this is the controller's regret, right? And this is my identification error. So you can bound the identification error of this least squares algorithm in terms of the controller's regret. And once you do that, we know by the lemma on identification, we can bound the performance of this identification algorithm. But we now can apply the meta-theorem to this ball, and we know that its metric entropy is roughly n squared dimension log 1 over delta. And then we use the metric as just the operator induced by the operator norm. Okay, so this is a careful adjustment of how many ball centers I need, and it's just square root is there because we have the squared error type performance criterion, and then we consider this kind of an estimator. Take that least squares identification algorithm and find its nearest neighbor in this packing set, and we can prove that the probability of error is at most 1/4 plus delta, and we assume that delta is less than a quarter. So by hypothesis on all our control algorithms, probability of error is less than half. But on the other hand, we have a lower bound on the probability of error through the meta-theorem. And the beautiful thing is that if I choose, so here's another useful choice of the auxiliary measure. Just choose what you would have had if you knew the system perfectly. If you knew the system perfectly, your optimal control is minus AX, and that leaves just the noise. So it means that at every step, your under that measure, your distribution of the state should just be the noise. So you just compare it to the noise, and in fact, it turns out to be precisely your performance metric scaled by the noise variance. And you just assemble everything and get this result. So quite a lot simpler than multidimensional integration. So here's a summary slide. The full paper is actually at this, as I said, it's a few years old, but still exploring all the implications of this and hopefully applying it to network systems soon. So.
For a break, a quick question.
Yeah.
Does the character building proof and the corresponding result assume the C delta
Yes.
conditioning?
Yes.
So this is a truly alternate way of getting.
Oh yeah, that's right. Yes.
Some of this minimax stuff, so if we think about, standard within the context of information theory, there's something kind of like Jeffrey's prior, which tells us that if we can pick the right sort of prior and look from a Bayesian perspective to do things. Is there something analogous in this setting where is there something kind of like a Jeffrey's prior?
So Jeffrey's prior would be useful in the context of ultimately doing something like universal prediction.
Yep.
Right? Here, though, what you're doing is that there's still a notion of least favorable prior. Jeffrey's prior is least favorable for problems over the entire set lambda. Here, because we're
somewhat analogous.
It's somewhat analogous, but because here we reduce it to finite hypothesis testing, least favorable prior is actually uniform over the packing set. I wouldn't be surprised if somehow
uniform prior, you're in some sense doing Jeffrey's prior.
I think if you adjust the separation radius at just the right rate, you will eventually have something like weak convergence to the Jeffrey's prior. I haven't looked at that, but I wouldn't be surprised if that were the case, in fact.
So there's some coffee outside, and if I could get